We've largely focused on calculating the stresses within three-dimensional structures, ones where we have stresses in all three directions emerging due to bending or torsion or pulling or pushing. In this section, what we're going to work on is looking at structures in which we can reduce the stresses that we evaluate from 3 dimensions to 2 dimensions. The first introduction that we're going to have to this concept is with pressure vessels. And these are structures that are all around us. Pressure vessels are basically thin-shelled structures that are able to withstand either high pressures within inside them or high pressures exerted on the exterior. This includes submarines, basketballs, airplanes, boilers, propane tanks. And so what we're going to do in this case is, instead of looking at the stress in all 3 directions, we're going to look at two directions of stress. And what we're going to do is neglect the stress through the thickness of the structure. And so this is called thin-walled pressure vessels. And so the first thing we need to know is, what do I mean by thin-walled? And thin-walled refers to the relationship between the radius of curvature, so that in this case is this little r, which goes from the centroid of the structure to the inner wall, and it's the relationship between that radius to the thickness of that wall. And so everything we're going to talk about today is valid as long as the ratio of the radius to thickness is larger than about 10. That leads to about a 4% error if it's around 10, and as you get to larger and larger values, that error decreases substantially. This is an important fact because if we get to thicker walled pressure vessels, then what happens is the equations we'll derive today will underestimate the stress within the structure, and that can lead to poor predictions of failure and structural integrity. We're going to focus on 2 cases. We're going to focus on the thin-walled cylindrical pressures and thin-walled spherical pressure vessels. For both the cylindrical and spherical pressure vessels, what we're doing is we're neglecting any through-thickness stress. And so if we consider the stress that goes through the thickness of the structure, if we call that sigma 3, so that's referring to any stress that's going on through this thickness, we're going to approximate that it's 0. And so we're only left with 2 stresses. The other thing that we're going to do, that's a little bit different to what we've done up until this point, is instead of focusing on stresses that run in the directions of the coordinate axes, so in this case they would run sigma x or sigma y, we're going to look at our stresses that run along the principal directions of the structure. And that sounds worse than it is. What that means is that we're going to kind of draw a plane on this structure. And the 2 stresses we're interested in are going to run along the circumference. We're going to call that sigma 1. And they're going to run along the longitudinal or axial direction. And that'll be referred to as sigma 2. And you'll notice that this sigma 1 doesn't follow the y-axis, it runs along the circumferential direction here, although in the case of a cylindrical pressure vessel, sigma 2 runs along that x-axis. And so we're interested in evaluating sigma 1 and sigma 2 for a pressure vessel. And so what we're going to do is we're going to take a slice here, and we're going to do this in 2 ways. The first thing we're going to look at is what's happening at sigma 1, that circumferential stress. The circumferential stress is equivalent to the stress that occurs when you tighten your belt buckle. It's a hoop stress. It's the compressive stress that's acting inward on a structure. And so we're going to look at that first. And in order to do that, we're going to make a couple cuts. And so we'll make 2 cuts here that are separated by a distance delta x. And then we're also going to cut along the x-axis here. And so what that sequence looks like if we redraw a free body diagram is simply structure like this. And so we can redraw everything we know on here, which is that our radius goes to this wall, that's R. We know this is our thickness. And this is a pressure vessel, which means there's going to be pressure acting in this direction here. And so let me just draw our coordinates for reference. We have our y-axis, running along the long axis is our x, and then coming out is z. And so this pressure is acting on this imaginary plane delta x that we cut. So here's delta x. And our pressure is acting on that plane. We're going to recut this in a minute and look at sigma 2 to see the pressure acting in the other direction. But for right now, let's focus on P acting on this plane. And in order for this to be in equilibrium, these walls right here and right here are going to have a stress coming off them. And so we can very simply draw a free body diagram. And now in this case we're interested in what's going on in the z direction. And so our free body diagram leads to our equilibrium equations in which we solve for the sum of the forces in the z direction, setting them equal to 0. And so what this looks like is we need to get our forces here. And so we have two different planes. So we have 2 times the force acting on those planes, and that force is going to be the stress times the area. The area is simply delta x times t, and so what you end up with is that 2 times sigma 1 times the thickness times delta x, and so this is our first force, and that's acting in the positive z direction, which is out of the board, and we're going to subtract off the pressure term, and that pressure term looks similar. It's a pressure acting on this. In this case here now it's acting on this whole kind of diameter of this, so it's going to act on 2 times the radius. And again, it's also going to act along the width of delta x. And we're going to set that equal to 0. When we do that, we can very quickly solve for our unknown, which is the stress in the one direction, the principal stress, sigma 1. This is our hoop stress, and we find that sigma 1 is going to be equal to P R over T. So that's pretty straightforward. This makes intuitive sense as well. This hoop stress is going to increase if the pressure increases, it's going to increase if the radius increases, and it's going to increase if the thickness of the shell decreases. So that should make a little bit of sense here. Now what we need to calculate is sigma 2. We need to determine if it's going to be larger or smaller than sigma 1, and that's going to lead us to be able to determine what's the kind of design criteria for our structures. So again, we'll need to draw a different free body diagram. If we kind of relabel these as A, B, and C, we're going to just look at this plane where we made a cut at B here, and we can draw our free body diagram for B. Now this is going to look fairly similar. Again, acting on this plane that we've cut here, in this case acting in the x direction, we're going to have our pressure, P. All along here we're going to have this wall which is exerting a stress because of that pressure. That's the longitudinal stress that we're interested in, sigma 2. Again, everything else is the same. We know that this is going to be our thickness, and we have our radius. And so again, once we have this free body diagram drawn, we can sum our forces. In this case, we're going to sum our forces in the x direction and set them equal to 0. We can make a little bit of a simplification here as well to make the math a little bit easier. We need to figure out the area that this sigma 2 is working over. And so the area that that's working on is a pi times r plus t. And that's going to be squared, and that's the area of the outer circle. We're going to subtract off the area of the inner circle to get the area that this stress is acting over. This is going to lead to a thickness squared term, and since one of the things we've assumed here is that our thickness is really small, we can neglect that squared thickness term, and so that we'll say that the area is approximately equal to a pi times r times t times 2. So it's just going to be that circumference of that inner circle times the outer thickness. And we're neglecting that t squared term, but that'll help. But that's reasonable in this thin structure approximation. So we can use that over here and do the same thing we did before, which is now our equilibrium equation looks like sigma 2 times our new area, which is going to be 2 times pi times r times t. And again, we're going to subtract off our pressure term. And that pressure is acting on the inner area of the circle here, and that's pi r squared. And that equals 0. Again, we can very simply solve for our other unknown, which is our longitudinal stress. And we see that sigma 2 is equal to P times R over 2T. And so we can immediately see that our hoop stress is always going to be twice as big as our longitudinal stress. This is going to be our factor we're going to need to consider when we're looking at when a structure is going to fail due to internal or external pressure. It's going to fail in this hoop direction, which means if this thing does exceed the stress, this stress in the one direction here is going to try and peel apart. And you'll see a fracture kind of along this longitudinal line. You see this in everyday use if you, say, cook a sausage. And if the sausage casing fractures because of the internal stress building up from steam, that sausage is going to fracture with a line in that direction. That's because that hoop stress is trying to peel that thing apart. So this is the cylindrical case, and the next thing we want to look at is the spherical case. And so we can do the same approach we had. We have this spherical shell, it's got a thickness, a radius. Again, I've kind of drawn on here that what we're really going to be interested in are not the kind of regular Cartesian coordinates, but the coordinates that go along this circle here. And so what that looks like, if we draw that on here, is we're interested in sigma in the 1 and 2 directions. And you'll note that since this is spherical, those sigmas should be equal to each other. So we just need to make one cut this time, and this time we'll cut along the y-z plane there. And we'll redraw this and draw our free body diagram. And again, we'll have pressures acting in this direction. And our stresses in the wall of the structure acting in the opposite direction. Everything else is the same. It's going to have a radius coming from the center to the inner wall and a wall thickness. And what you might immediately recognize is that this free body diagram looks exactly the same as the free body diagram we drew for sigma 2 in the case of the cylindrical pressure vessel. And it turns out that this is going to have the exact same relationship for the principal stress, and it's that the stress in the 1 and 2 direction are going to be equal, and they're going to equal the longitudinal stress here. So you get the same free body diagram, which means you get the same equilibrium equations, which means as you solve for sigma 2, what you end up with is that for a spherical pressure vessel, your principal stresses are equal, and they're equal to that longitudinal stress, which is PR over 2T.